Okay, exercise 1.7 deals with graphing exponential functions. We also have, there's a few notes you've already seen on exponential functions in the differentiation notes. What we're looking at here is we want to plot the graph of y is equal to 2 to the power of x between -3 and +3. An exponential function, by the way, is when you have an x in the power. So if we want to graph y is equal to 2 to the power of x, what we do is we say, we sub in -3 for x. So in other words, you'd have 2 to the -3, which is 1 over 2 cubed, which is in fact 1/8. Um, 2 to the -2 is, if you evaluate, a quarter, because it's 1 over 2 squared. 2 to the -1 is a half. 2 to the 0 is 1. Again, it's worth bearing in mind that anything to the power of 0 is a 1. Just come to that later, that's quite significant. 2 to the power of 1 is just a 2. 2 squared is a 4, and 2 cubed is an 8. So just a really rough sketch. When x is 0, y is going to be equal to 1, and that's true of any exponential function, because anything to the power of 0 is always equal to 1. So when x is equal to 0, y will always be equal to 1. If we go back here, I'm just, again, very roughly, -3, so you're way down here at an 1/8. -2, you're at a quarter. Again, not to scale, this is just to show you that it's just gradually getting bigger. When we're at 1, you have a 2. Again, very rough. When you're at 2, you're at a 4. And when you're at 3, you're at 8. So it starts to rise quite steeply from then on. So it kind of looks something like this. Smooth curve, obviously, it's very difficult to do this on the computer. Just to note that the x-axis is what we call an asymptote. So if you were to continue on down here, the graph would always head towards the x-axis, would never quite get there. And also then the point 0, 1 is on the graph always, because any 2 to the 0 is equal to 1, or any number to the power of 0 will be equal to 1. So that point there is common. 0, 1 is common to all power graphs. If we look at related graphs, for instance, 2 to the x compared to 3 to the x compared to 4 to the x, you might be, so this is the red one is 2 to the x. You might think that 3 to the x would be out in this direction here, but it's not. It actually has the effect of making the graph steeper, okay, because the y values are going up much faster if it's 3 to the power of x. Similarly, 4 to the power of x will be steeper again, and so on. Now you want to consider what the graph looks like if you have got y to the power of something to the power of x, if this something is a fraction. So for instance, we've got y is equal to a half to the power of x, and we want to graph it between -3 and +3. Okay, so what you get here is if you put in -3 for x, you have 1 over 2 to the power of -3, which is in fact, it's 1 over 1/8, which evaluates in fact to 8. Just gonna do this. So we get an 8 in here. And then 1 over 2 to the -2 is 1 over a quarter, which evaluates to a 4. 1 over 2 to the -1 evaluates to a 2. 1 over 2 to the 0 is equal to 1. 1 over 2 is a half. 1 over 2 squared is a quarter, and 1 over 2 cubed is 1 over 8. Now again, very rough sketch. Of course, we still have this common point 0, 1, like we had before. If we go in the minus direction, the numbers are increasing, okay, and if we go in the positive direction, the numbers are decreasing. So again, I'm just very roughly, this is going to be half, a quarter, 1/8, so it kind of looks like this. This is going to be a 2, then a 4 doubling, and then going right up, okay, so just a very rough graph looks like this. And that is true of any graph where you have a fraction to the power of x. Here's a general way of saying that. So if the number is you know, like you have y equals 2 to the x, for instance. If the number here is greater than 1, then it looks like this. Whereas if you have a fraction in this position, the graph is going to look like that. Now looking at graphing log functions. Okay, so for instance, we're going to graph the function y is equal to log to the base 10 of x between 0.1 and 5. So we start out, and again we can do this with our calculator if we want. It's probably the easiest thing. If you get the log of 0.1, it's -1. If you get the log of 1, it's 0. If you get the log of 2, it's 0.3. The log of 3 is 0.47. The log of 4 is 0.6. And the log of 5 is 0.69. Now what happens with the log function is, if I'm to draw it, okay, we go 1, 2, 3, 4, 5 approximately. Okay, at 0.1 you're at -1 down here. Okay, it's kind of hard to draw to scale. You get a crossover point, crosses the x-axis at 1. At 2 it's 0.3, and it's just very gradually increasing as you get to here. Now, it's sort of interesting on this side, what happens is that you get a very steep kind of drop off here, and the y-axis is an asymptote whereby the graph tends towards the y-axis but never actually gets there. Just to let you know, the inverse of the graph y is equal to log to the base 10 of x, which we've just drawn, is actually 10 to the power of x, and we've come across before, to get the inverse of a function, you simply mirror it in the line y is equal to x. So if this is the function y is equal to log to the base 10 of x, its inverse, which is y is equal to 10 to the power of x, is a mirror image in the line y is equal to x. And just to note then, the x-axis is an asymptote for the line y is equal to 10 to the power of x. Similarly, the inverse of y is equal to log to the base 2 of x is y is equal to 2 to the power of x. Natural logs we've come across before, and we've said that it's a sort of special log function, which again we're going to I'll dwell on this later. But what it's log to the base e of x, and it could also be written ln of x. And just to notice that e is a particular number, 2.718, etc. So it's okay. Again, we will do more about that at another point. For now, if you do exercise 1.7, questions 1, 3, 14 and 15, that should cover you. Now there is more in the book about logs and log functions, but I'm going to do that in class.